According to the 1999 National Electrical Code, specifically Article 384.3A3, bus bars must be enclosed to provide a dead front assembly under certain voltage conditions. If the maximum voltage does not exceed 150 volts to ground or 300 volts between conductors, the requirement is enclosure for dead front assembly. However, when the maximum voltage surpasses 150 volts to ground or 300 volts between conductors, the code mandates that bus bars be both enclosed and guarded to achieve a dead front assembly. This regulation aims to protect personnel from accidental contact with live conductors, reducing the risk of electrical shock and arc flash hazards. The purpose of a dead front assembly is to prevent unintentional contact with energized components. This is achieved by ensuring that all live parts are inaccessible from the front of the equipment, thus enhancing safety during operation and maintenance. Enclosing and guarding the bus bars creates a physical barrier, preventing accidental contact and minimizing the potential for electrical incidents. Furthermore, Article 384.10 of the 1999 National Electrical Code addresses the protection of conductors entering a bus enclosure. This section stipulates that conductors entering a bus enclosure must be protected against physical damage. The intent here is to safeguard the insulation and integrity of the conductors, ensuring that they are not compromised by abrasion, sharp edges, or other potential hazards within the enclosure. Protecting conductors against physical damage is crucial for maintaining the reliability and safety of the electrical system. Damaged conductors can lead to short circuits, ground faults, and other electrical failures, which can result in equipment damage, power outages, and even fire hazards. Therefore, proper protection of conductors entering a bus enclosure is essential for preventing these types of incidents. In the described scenario, a 480-volt motor control center, or MCC, is configured in a U-shape with corner sections at 45 degrees. The bus bars extend horizontally through these corner sections. The electrical contractor has installed conduits in the slab, which stop into this 45-degree section. During wire pulling, the bus bars are exposed to the conduits and wires. This exposure raises concerns regarding compliance with the National Electrical Code, specifically the articles mentioned earlier. Given that the voltage of the MCC is 480 volts, which significantly exceeds the 150 volts to ground or 300 volts between conductors threshold, the bus bars must be both enclosed and guarded to provide a dead front assembly, as mandated by Article 384.3A3. The exposure of the bus bars to the conduits and wires during wire pulling introduces a risk of physical damage to the bus bars. This situation directly contravenes the requirements outlined in Article 384.10, which necessitates that conductors entering a bus enclosure be protected against physical damage. The absence of a barrier between the bus bars and the conduits and wires creates a potential for abrasion, insulation damage, and even direct contact, which could lead to short circuits or ground faults. To ensure compliance with the National Electrical Code and to mitigate the risks associated with exposed bus bars, it is imperative to install a barrier around the bus bars in the 45-degree section of the MCC. This barrier should be constructed of a non-conductive material that is capable of withstanding the environmental conditions present in the MCC. The barrier should be designed to completely isolate the bus bars from the conduits and wires, preventing any physical contact. Firstly, the barrier should be made of a material that provides adequate electrical insulation to prevent short circuits or ground faults in the event of accidental contact. Secondly, the barrier should be robust enough to withstand physical impacts and vibrations that may occur during normal operation of the MCC. Thirdly, the barrier should be properly secured to the MCC enclosure to prevent it from dislodging or shifting over time. The installation of a barrier around the bus bars not only ensures compliance with the National Electrical Code but also enhances the overall safety and reliability of the electrical system. By preventing physical damage to the bus bars and conductors, the barrier reduces the risk of electrical failures, equipment damage, and potential hazards to personnel. Furthermore, the barrier contributes to the longevity of the MCC by protecting its critical components from environmental factors such as dust, moisture, and debris. In conclusion, based on the information provided in the relevant articles of the 1999 National Electrical Code, the installation of a barrier around the bus bars in the 45-degree section of the 480-volt motor control center is necessary to ensure compliance with the code and to mitigate the risks associated with the exposed bus bars. This barrier should be designed and installed in accordance with industry best practices and should meet all applicable safety standards. By implementing this measure, the electrical contractor can ensure the safety and reliability of the electrical system and prevent potential hazards to personnel and equipment. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in technology and safety practices. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their built-in codes. Compliance with the NEC is essential for ensuring the safety of electrical installations and preventing electrical hazards such as fires, shocks, and explosions. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for the selection and installation of electrical components, as well as guidelines for safe work practices. The NEC is organized into chapters, articles, and sections, making it easy to find specific information on a particular topic. Each article covers a specific area of electrical installation, such as wiring methods, overcurrent protection, or grounding. The NEC also includes tables and examples to help clarify the requirements and provide guidance on how to comply with the code. In addition to the NEC, there are other standards and regulations that may apply to electrical installations, such as those issued by the Occupational Safety and Health Administration, or OSHA, and the National Fire Protection Association, or NFPA. It is important to be familiar with all applicable standards and regulations to ensure that electrical installations are safe and compliant. When working on electrical installations, it is essential to follow safe work practices to prevent electrical hazards. This includes de-energizing equipment before working on it, using appropriate personal protective equipment, or PPE, and following lockout-tagout procedures. It is also important to be aware of the potential hazards associated with electricity, such as arc flash and electrical shock, and to take steps to mitigate these risks. Arc flash is a dangerous phenomenon that can occur when there is a short circuit or other fault in an electrical system. Arc flash can produce intense heat, pressure, and light, which can cause serious burns, eye injuries, and even death. To protect against arc flash hazards, it is important to wear appropriate PPE such as arc-rated clothing, gloves, and face shields. Electrical shock is another potential hazard associated with electricity. Electrical shock can occur when a person comes into contact with a live conductor or other energized component. Electrical shock can cause muscle contractions, burns, and even cardiac arrest. To protect against electrical shock hazards, it is important to de-energize equipment before working on it and to use appropriate PPE such as insulated gloves and tools. Lockout-tagout procedures are used to prevent equipment from being accidentally energized during maintenance or repair. Lockout-tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. This ensures that the equipment remains de-energized while work is being performed. In addition to following safe work practices, it is also important to properly maintain electrical equipment to prevent electrical hazards. This includes regularly inspecting equipment for damage, cleaning equipment to remove dust and debris, and repairing or replacing damaged components. Proper maintenance can help to prevent electrical failures and extend the life of electrical equipment. When selecting electrical components, it is important to choose components that are rated for the voltage and current levels of the system. It is also important to choose components that are listed by a recognized testing laboratory, such as Underwriters Laboratories or ALL, or Electrical Testing Laboratories, or ETL. Listed components have been tested and certified to meet safety standards. When installing electrical wiring, it is important to follow the wiring method specified in the NEC. This includes using the correct type and size of wire, properly supporting and securing the wiring, and making connections in accordance with the code. Improper wiring can lead to electrical hazards such as short circuits, ground faults, and fires. Overcurrent protection is used to protect electrical circuits from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a certain level. This helps to prevent overheating, damage to equipment, and fires. Grounding is used to provide a safe path for fault current to flow back to the source in the event of a ground fault. Grounding helps to prevent electrical shock hazards and to protect equipment from damage. The NEC specifies detailed requirements for grounding electrical systems and equipment. Special occupancies such as healthcare facilities, hazardous locations, and swimming pools have additional requirements in the NEC to address the unique hazards associated with these environments. It is important to be familiar with these requirements when working on electrical installations in special occupancies. Healthcare facilities have requirements for essential electrical systems to ensure the critical equipment remains operational during power outages. Hazardous locations have requirements for explosion-proof equipment and wiring methods to prevent explosions and fires. Swimming pools have requirements for ground fault circuit interrupters, or GFCIs, to protect against electrical shock hazards. The NEC is a complex and comprehensive document that requires careful study and understanding. It is essential for anyone working on electrical installations to be familiar with the NEC and to follow its requirements to ensure the safety of electrical installations and prevent electrical hazards. Continuous learning and staying updated with the latest revisions of the NEC are crucial for electrical professionals to maintain competence and ensure compliance with the evolving standards. The NEC serves as a cornerstone in safeguarding lives and property from electrical dangers, and adherence to its guidelines is paramount in the electrical industry. The interpretation and application of the NEC can sometimes be challenging, requiring a thorough understanding of electrical principles and the specific requirements of the code. Consulting with qualified electrical inspectors and engineers can help to ensure that electrical installations are compliant and safe. Electrical inspections are an important part of the electrical safety process. Electrical inspectors review electrical installations to ensure that they comply with the NEC and other applicable standards. Electrical inspections help to identify and correct potential electrical hazards before they can cause harm. It is important to cooperate with electrical inspectors and to address any issues that they identify in a timely manner. Addressing the specific scenario, the recommendation to install a barrier around the bus bars in the 45-degree section of the 480-volt motor control center aligns with the principles of electrical safety and the requirements of the National Electrical Code. The barrier serves as a physical safeguard, preventing accidental contact with energized components and protecting the bus bars from potential damage. This measure enhances the overall safety and reliability of the electrical system, minimizing the risk of electrical hazards and ensuring compliance with industry standards. The decision to implement this safety measure demonstrates a commitment to electrical safety and a proactive approach to preventing potential incidents. By prioritizing safety and adhering to the requirements of the National Electrical Code, the electrical contractor can create a safer working environment and protect personnel and equipment from electrical hazards. The long-term benefits of implementing this safety measure outweigh the initial cost and effort. By preventing electrical failures and equipment damage, the barrier can help to reduce downtime and maintenance costs. It can also help to improve the overall efficiency and reliability of the electrical system. In addition, the barrier can help to protect the reputation of the electrical contractor by demonstrating a commitment to safety and quality. Clients are more likely to trust and rely on contractors who prioritize safety and adhere to industry standards. The installation of a barrier around the bus bars is a proactive step that can help to prevent accidents, protect personnel, and ensure the long-term reliability of the electrical system. It is a worthwhile investment that can provide significant benefits in terms of safety, efficiency, and cost savings. The design and construction of the barrier should be carefully considered to ensure that it meets the specific requirements of the application. The barrier should be made of a durable and non-conductive material that is capable of withstanding the environmental conditions present in the motor control center. It should also be designed to provide adequate clearance around the bus bars to prevent accidental contact. The installation of the barrier should be performed by qualified electrical personnel who are familiar with the requirements of the National Electrical Code and other applicable standards. The installation should be carefully inspected to ensure that it is properly installed and that it provides adequate protection for the bus bars. After the barrier is installed, it should be regularly inspected to ensure that it remains in good condition and that it continues to provide adequate protection. Any damage to the barrier should be repaired promptly to prevent electrical hazards. The barrier is an essential component of the electrical safety system and should be treated with care and respect. The National Electrical Code is a living document that is constantly evolving to reflect the latest advancements in technology and safety practices. It is important for electrical professionals to stay up to date with the latest revisions of the code and to implement any necessary changes to their electrical installations. The National Electrical Code is a valuable resource that can help to ensure the safety of electrical installations and prevent electrical hazards. By following the requirements of the code and implementing appropriate safety measures, electrical professionals can create a safer working environment and protect personnel and equipment from electrical dangers. The commitment to electrical safety is an ongoing process that requires continuous learning, vigilance, and a proactive approach to preventing potential incidents. By prioritizing safety and adhering to industry standards, electrical professionals can make a significant contribution to the safety and well-being of their communities. The installation of a barrier around the bus bars in the 45-degree section of the 480-volt motor control center is a clear example of how to implement electrical safety best practices and ensure compliance with the National Electrical Code. This measure demonstrates a commitment to safety and a proactive approach to preventing potential hazards. By following this example, other electrical contractors can improve the safety of their electrical installations and protect personnel and equipment from electrical dangers. The barrier needs to be properly rated for the environment it is in as well. If it is in a corrosive environment, the barrier will need to be made of corrosion-resistant material. If it is in a high-temperature environment, the barrier will need to be made of a high-temperature resistant material. The barrier also needs to be properly grounded to prevent the buildup of static electricity. Static electricity can be a hazard in some environments, as it can cause sparks that can ignite flammable materials. The grounding of the barrier will help to dissipate any static electricity that may build up, preventing sparks from forming. The barrier must not impede the airflow into the electrical panel because heat will build up. The higher the heat, the more the bus bars degrade. The more they degrade, the more they loosen and could cause a catastrophic failure. The barrier is meant to protect against someone accidentally touching the bus bars or other wires touching the bus bars. Make sure that the access to the conductors are not restricted either, because any repair work would be difficult to do. The barrier should be easy to remove and reinstall. Make sure the barrier is properly labeled as a safety barrier. This is to notify people that the barrier is there for safety reasons and should not be removed unless necessary. The label should be easy to read and understand. The label should also be durable and weather resistant.